Reisenhuber, and I'm the Education Coordinator for the NASA Oklahoma Space Grant Consortium. And today, we are bringing you another exciting aviation demonstration. Now, as you may remember, our last two videos have included demonstrations that also deal with aviation. And each of these videos build upon the concepts, which are going to take us further and further into understanding engineering design. And you guys so far have been incredible aerospace engineers, and I cannot wait to see what you engineer in this next demonstration. But let's review what we've learned so far. So during our first video, we learned that there were numerous properties of air. We focused on 4, and we even kind of streamlined our focus more on that air exerts pressure. And that was extremely important to take us into the second part of that first video, in which we experimented with a variety of items in Bernoulli stations. And we learned what Bernoulli discovered hundreds of years ago, and that was that the faster the air, the lower the pressure, and the slower the air, the greater the pressure. And it was really cool to see it happen in 6 different things. Then we took that one step further in our second video, and we looked at how Bernoulli's principle is linked to the wing of an airplane, or the shape we also call an airfoil. And what we learned that this wing is shaped so that the top is curved, and it compresses or makes the pathway smaller for that air. So the air coming across, when it's compressed, we know that that speeds up air. And then from Bernoulli's principle, we know that when that air is sped up, it decreases the pressure. But below, we have not compressed the path at all. And so that air is just traveling along at that slower speed, which creates greater pressure. And then we have what we call lift. And we learned that not only is lift one of the 4 forces which is acting upon the plane, it is that upward force, lift, but we also learned with our wing on the string that as we added more weight, we could actually zero out lift. So if you add enough weight to your wing, and I'm just going to use this binder clip as my demonstration for the weight, but as we add more and more weight to it, we start to zero out that lift. So weight is the downward force acting upon the plane. And you know what? There are 2 more forces that we can learn about that are acting upon that plane. And we're going to learn about those today. So for the first force that we're going to learn about, we are going to want to build what is called a foam rocket. And for that rocket, first I'm going to have to grab one more item that I realize I do not have on my table, and that is some scissors. So for this activity, you can use a variety of materials. You will definitely need scissors or something to cut with. For the body tube, you are going to need either foam pipe insulation or a pool noodle, or you could even use a paper towel tube. Now, because of the properties of a paper towel tube are very different from these foam tubes, it is going to change how you're going to have to experiment with it. And we'll talk about that a little bit when we actually do the experimentation of our foam rocket. But again, anything cylinder, you can make work for this. For this first part, it doesn't really matter the length. All of my foam pipe insulation pieces are the same length. For this first part, you only need 1. But I've made sure that all of mine are the same length because that's going to be important into the second part of our experiment. You're also going to need either foam or cardstock or something that you can use for the fins. Definitely want something a little bit firmer than paper, just regular printer paper, notebook paper, but again, cardstock, poster board, fun foam, anything like that will work. And then we're going to need tape, preferably duct tape. You could use masking tape, scotch tape, any of those tapes, but over time, those are going to degrade a little bit faster and maybe are going to have to be repaired more often. And so I recommend duct tape if you want something that's going to last over and over and over again. You're also going to need a protractor. That's going to be very important when we are launching our foam rocket. And you are going to want a yardstick or a meter stick. to also help in the launching of it. Now there's one more thing in the construction of it that you're gonna need, and it is these rubber bands. Now you'll notice these are thicker rubber bands. They're not the thin little rubber bands, and that's also important. That's gonna help create longevity in your rocket, because those smaller ones, the more and more that you are launching this, those could break. Okay, so let's get started with our construction of this first rocket. So the first thing that I'm gonna do is I'm gonna take one of my pieces of foam, because that's all I'm gonna need to make this first demonstration, and I'm gonna notice that there is a seam on my rocket. And I'm just gonna avoid that because I don't wanna cut it and then it just keep going all the way up further than I want it to cut. So I'm gonna go just to the left of that seam where it has been glued together. And I'm gonna cut it straight up, directly to the left of that seam. And as I do that, I'm gonna make sure that I cut the full length of my scissors. Now something else that I could do to ensure that I'm making them all the same length up is I could also measure that with my yardstick or my ruler or whatever measuring device I had available. So this is about 3 1/4 inches. 3 1/4 inches. So I'm gonna try to keep that consistent on all of them. So I cut one slit into my rocket or into my foam body tube of my rocket. And I'm gonna go to the opposite side. Now, I know that circles don't have sides, but for this, just to help us know which direction and where we're cutting each of these items, we will be talking about it as if a circle had sides. So I'm gonna go to the opposite side of that circle, and I'm going to cut straight up. And then I'm gonna measure and make sure I'm about 3 1/4 inches. And that one did not quite go as much, which is another reason why it's really good. I'm measuring these. And let's see, that one's 3 1/4 now. Excellent. Now I'm gonna go directly in between each of these slits. So I'm gonna do that on one of them. So I'm gonna go straight down the middle, and this is gonna be approximate, right? Because I'm just kind of eyeing it, and that's okay for this part of our experimentation. And let's see, looks like I need to go up just a tad bit, not much. So I'm gonna take it up just a little bit more. And that should put me at 3 1/4. Excellent. And then I'm gonna go on the opposite side, and I'm gonna go up the exact same amount. And that should give me about 3 1/4. And that is 3 1/4. Excellent. So I now have 4 slits that are all 3 1/4. So it's kind of like 4 or half of the octopus legs that an octopus has, because an octopus has 8 legs. But our fin well is going to have 4 little areas to put a fin in. Excellent. So the next thing that I need to do is I'm going to need to create my fins. So when I create this one, I'm already keeping in mind what I'm going to need for the next experiment. But you could make these any shape that you want, any which way that you'd like. And we're actually going to talk about that. We're going to revisit this experiment and look at fin design on it in a couple more videos. So later on in all of the distance learning videos, you are going to get to see how to use this for engineering fin design. But for this one, I'm going to take one piece of cardstock. That's what I chose. Now, if you do not have a nice little cutting board like I do, you could also use a ruler and pencil and measure this out. But to kind of speed it up for television, I'm going to go ahead and use my paper cutter. So I know that I can measure on this paper cutter, and I know that the length of my paper is 11 inches. So I'm going the long side, or the burrito side of my paper, and that is 11 inches. Now I'm going to turn it to my shorter side, or my taco side, and I'm going to want to make those fins. I'm going to want to make them 2 inches tall, or 2 inches wide, whichever way you want to look at it. So I'm going to make 2 of them. So I've got one, and now I'm going to make a second one, and I want to try to keep those as straight as possible, and in my lines as straight as possible. So if you are using a ruler and scissors on your cardstock to measure out instead of a cutting board, you're going to need to make sure that you get those lines as straight as possible, because it's going to be really important that we limit our variables as much as possible. And sometimes there's just gonna be that human error factor, and it plays into most experiments. But we wanna try to limit that as much as possible. So now that I have two fins, I'm gonna put them together, and you can see that my fins are almost the exact same. I'm gonna go ahead and leave these fins as 11 inches long. And now we will experiment with the length on others here in just a few minutes. But for this one, we're gonna keep them 11 inches long, and they're 2 inches wide or 2 inches tall, however you wanna look at that. So the next thing I'm gonna do is I'm gonna take my scissors, and I'm gonna want to cut halfway up both of these pieces of cardstock fin together. And so I'm gonna cut, well, let's find out where my halfway point is. So my halfway point is, so 11, if I divide 11 and a half, that's 5.5. So 5.5 plus 5.5 equals 11 if you do that math. And I'm gonna wanna cut halfway up on that piece at my 5.5 inch mark, or the halfway point. So when I cut about halfway, I may have actually just cut a little over, but that's okay, that won't matter. If I cut under, I don't wanna cut under, but if I cut a little over, it's gonna be okay. You'll see that in just a minute. But as close as I can possibly get to going exactly halfway, or 1 inch, I guess is how we could look at it since it's 2 inches across, 1 inch down. So the next thing I'm gonna do is, now that I've created two fins, I am going to put those fins together so that they look just like this. How cool is that? Okay, so now I have 4 fins, super easily done, and I can put them into my little fin well. Excellent. And they fit just like this. Now, if you'll notice, there's nothing holding these fins in. So let's get those fins stuck in place. So the next thing that I'm gonna do is I'm going to take my duct tape and I am going to take it just like so, and I just cut off a strip which is about this long. Now I'm gonna go ahead and measure this strip because I'm gonna wanna know that for the future ones that I make and do. And I may actually change this and measure it exactly. So that was a mistake I made, but you're getting to see the exact same things that happened with the Wright brothers as they were doing their experimentation and trying to figure everything out. And I got lucky because this is 10 inches long, exactly, so excellent. Now we'll put that, ours is actually a yardstick, so we'll put that over there. We are going to cut this piece of tape in half. And you're gonna wonder, why are you doing that? Well, it's actually gonna make it a lot easier to make sure that I don't put too much extra material hanging off of my rocket. So that's gonna be very important, that we want to limit the amount of material hanging off of our rocket. We just want the material hanging off really to be these fins. So the next thing I'm gonna do is I'm gonna take my tape and I am going to wrap it around that bottom. And I'm kind of holding these fins together as well as I can to try to keep it together as much as possible. So now you can see I have this little rocket, and I'm gonna go ahead and finish out wrapping the rest of my duct tape around that rocket. And the next thing I'm gonna do is I am going to push that tape down. You see how I did that? Okay, so now my rocket, my fins are in the body tube of the rocket and they're not gonna come out. The next thing I've gotta do is I've gotta create the device by which I'm going to launch this rocket. And instead of having fuel per se, my fuel is going to be a rubber band and the force created by pulling back a rubber band. So the first thing I'm gonna wanna do is I'm gonna want to cut a piece of duct tape. Now for this piece of duct tape, I'm gonna cut it 5 inches long. And so I'm actually just gonna use my cutting board right quick because I can put it on here. I'll start it at the 5-inch mark. If I'm wanting to make it 10 inches long, I'm gonna cut it at, I'm gonna start at the 5-inch mark. If I'm wanting to make it 5 inches long, I'll cut it at the 10-inch mark. So see how I did that math? Math is really important as an engineer. But you've got that going. Now the next thing that you're gonna do is you're gonna take this piece of tape, this 5-inch piece of tape, and you're gonna fold it in half like so. So I'm gonna fold it just like this. Does everybody see that? Okay, so now that my piece is folded just like so, I am going to, let's see, take my rubber band and I'm going to stick this piece of folded duct tape over top of my rocket. And I'm gonna wanna make sure that it has my rubber band directly against my foam rocket. I'm not gonna want a lot of extra space. And that's important here in just a minute and you'll understand why. So the next thing that I'm gonna do is I'm gonna take that other half of that piece of tape that I used to tape the fins in down here. I'm now gonna use it to tape this in place. So now I have this really cool foam rocket. The next thing that I'm gonna wanna do is I'm gonna have to create my launch device. And for this launch device, I'm gonna wanna make sure that when I launch it, I'm controlling which angle by which I launch it and also how far I pull it back. And so in order to do that, I am going to use this protractor as my base on my yardstick. And then I am going to go to the 40-degree angle mark. Actually, let's go ahead and do the 60-degree angle. I think that would be better. And I'm gonna do this in a way in which the protractor is actually gonna be the base. And I'm gonna have to take my duct tape. Now I could really use some extra hands, right? It's too bad during COVID, we have to learn how to do a lot of things on our own, don't we? And become a little bit more independent on figuring out creative ways by which to make things work that we used to do with 2 people in the room. So now that it is directly at that 60-degree angle, I am now gonna take my tape and tape it in place. So now I'm gonna be able to launch my rocket on my launcher and be able to make sure that angle is the same each and every time. So let's check that out and see how that works. So let's see, I'm gonna see if I can get you in. I can't quite do that, so let's see if I can do it from here. Okay, so you can see us really well there. And I'm gonna take this rubber band and I'm gonna place it over my yardstick, just like so. And as I do that, I am now going to launch it and see what happens. What happened? Well, our rocket went forward. And that forward movement is what we call thrust. And thrust, oh my goodness, that is that third force which is acting upon the plane. And so thrust is what makes the plane go forward. So forward. Thrust is that force acting upon the plane which causes it to go forward. So I talked about a force that's acting upon the plane which causes it to go upward, which is lift. And we've talked about the force which acts upon the plane downward, which is weight. And we've talked about the forward one, which is thrust. So I wonder what is pulling it backwards. Well, let's take this one more step with our experimentation. Are you guys ready? Let's try it out. So one rocket helped us understand the forward force working upon an airplane, which is thrust, and that's what propelled my rocket forward. But now we're gonna look at a fourth force acting upon that airplane. And in order to do that, we're gonna have to create 2 more rockets. So very quickly, kind of following along what I've already done, I've already kind of pre-cut some things, but I'm gonna quickly go through and make those fin wells for each of those areas on my rocket. And I'm gonna make sure that each of those are 3 1/4 inches long. Let's see. Oh, yep, I got that. And then I'm gonna come in here and go on the opposite side. And I'm gonna make sure again that that is 3¼ inches long. Let me move that this way. Let's see. Yep, 3¼ Then I'm gonna go halfway in between that slit. And I am going to make another 3¼ slit up my rocket. Yep. And I'm gonna make a 4th and final slit up that rocket, which is going, or that body tube of my rocket. Gotta use my good rocketry terms when I'm building a rocket. And now that I've got all of those in, I'm gonna need to look at fins. Now this time, I'm gonna experiment with the length of my fins, or the amount of material I have on my rocket. And I wonder how that's gonna affect things. So to do that, I'm actually gonna take these 2 pieces of cardstock together, and I'm going to cut twice, so I'll have a total of 4 fins. But I've got, let's see, my 2-inch. So I'm making them 2 inches wide. I'm keeping that I'm not changing that. I want as few variables as possible. So I want to keep that constant, that is going to be 2 inches wide or 2 inches tall on those fins. I'm gonna do that one more time. Just like so. So now I have 2 fins, which are each 2 inches wide. I have 2 sets of fins. I guess I should say 4 fins total. Now I'm gonna cut these different lengths so that my fins are different lengths. So this first one was 11 inches, and this next set is going to be a little bit shorter. So I'm gonna make it 7 inches, and just like so. So those are gonna be 7 inches long. And then this next one, I'm gonna go down another 4 inches because I have 11 inches, 7 inches. So now I'm gonna go down to 3 inches. All right, so since you guys already know how to construct these, I am going to get busy finishing up these last steps of constructing each of these rockets. And then I'm gonna show you my experimentation, and we're gonna talk about what's occurring, and we're gonna wrap it up together. So the next time that you catch me, I'm gonna have 3 rockets, 1 rocket with 11-inch fins, another rocket with 7-inch fins, and a 3rd rocket with 3-inch long fins. So check out this next segment. All right, so now we are ready to launch these rockets. And as you can see, I have my rocket that we made in our first demonstration. That's the rocket that has the 11-inch long fins. Then the one that I partially made on camera, which was our 7-inch long fins, and the one I made off camera, which is our 3-inch long fins. Now, as you can notice, almost everything else is the exact same. There may be a little bit of human error on each one of these, but for the most part, they are the same, except for the amount of material which was used for the fins, or the amount of surface area of fins. So let's test it out and see what happens. So the first thing that I'm gonna need to do is I'm gonna need to make sure that my launch device is prepared. Now, as you can tell on my launch device, I've changed it, where now the bottom of my yardstick is matching up with a 30-degree angle. And when I get over there, I'm gonna make sure that that is the exact same for each of those. So I wanna make sure that my trajectory, or the angle at which I am launching these rockets, is the exact same for each of these launches. Okay, now I'm gonna go back a little bit, and I'm gonna try to be as loud as I can so you can hear what I'm doing. So I'm gonna come back to my table. When I'm at my table, I'm gonna find a spot on my table that I'm always going to start from, so that way I'm sure I'm using the exact starting point on this table and making that the same for each of these rockets. Then I'm going to take my first rocket. Actually, I'm going to go back just a little. I don't know if you can see how well you can see our launching all the way back here. But it's going to be similar to what we did in the first demonstration. So I'm going to take this first rocket, and I'm going to go back 6 inches. I'm going to make sure that my angle has not moved. I'm still at a 30-degree trajectory. And I'm going to take those longest lengths of fins. I'm going to hold it from behind so my fingers don't get in the way. And let's see what happens. 5, 4, 3, 2, 1, blast off. All right, so that rocket went pretty far. Well, I wonder also at a 30-degree angle, so my trajectory is at 30 degrees. And 5, 4, 3, 2, 1, blast off! Okay, that one went a little bit further, didn't it? So now for our final one, and again, I want to keep a lot of things the same. I want to keep my trajectory the same. I don't want that to be a variable in this experiment. And I'm going to make sure I'm starting at the exact same point I did at the others. I'm going to hold it from the bottom, and I'm going to go back 6 inches, and let's see what happens. 5, 4, 3, 2, 1, blast off! Oh my goodness, so that one went further. So we learned that our 11-inch fins, which there was more fins for, it did not go as far. But our rocket with 7 inches went a little bit further. But the one which went the furthest is this rocket, which had only the 3-inch fins. Oh my goodness. So I think what we just learned is that the less amount of material or hanging off of my rocket, the further it went. Oh my goodness, you guys are so smart. You have discovered the 4th force acting upon an airplane, and that is drag. Well, let's wrap that up and see how all of these forces work together. So let's wrap up what we just learned by launching those rockets. So we learned in our first demonstration today that thrust is what causes the plane to go forward. And so when I pulled back on that rubber band, it created tension. And when I let go, that created a force which propelled that rocket forward, or thrust my rocket forward. Then we took it one step further, and in addition to our 11-inch long fins, we also created a 4-inch fin, a 7-inch fin foam rocket and a 3-inch fin foam rocket. And what we learned from that was that the more surface area, or the longer those fins, the more material that there was, it didn't go as far. And the less material there were of the fins, the farther it went. And boy, did this one go far. And so we were able to understand how drag, or increasing the amount of drag, increasing the amount of material, can slow down a plane. Oh my goodness, you guys are such brilliant aerospace engineers. So until I see you next week, race you to the moon.